We introduced FARO, a platform for automated adaptive optogenetic targeting. Optogenetic uses light to precisely activate signaling in live cells. Most of these experiments rely on manually drawn illumination patterns, which limits throughput and reliability. FARO automates this. It continuously segments and tracks cells in real time, updating the light patterns on the fly even as cells move or change shape. This approach scales to hundreds of cells in parallel, allowing us to guide and arrange cells into user-defined shapes, like a dynamic tissue printer. In this experiment, we use an optogenetic TRKA actuator. Running 24 fields of view in parallel for 2 days, FARO guided NIH-3D3 fibroblasts into user-defined letter shapes. Zooming in, we can see how every cell is segmented, tracked, and assigned its own continuously updating light mask, based on a few rules. For example, cells that overlap the target shape are anchored in place, stray cells are steered in, and surplus cells are pushed away once the shape is full. How did we find these rules? Each failed strategy on the real microscope would cost us a full day, so we built a virtual microscope, an agent-based simulation where cells respond to light, like in the real experiment, letting us iterate in hours instead of weeks. We even used large language models to translate high-level instructions like steer cells only towards 3 regions of the target directly into working control code. This makes it possible to program complex cell behaviors in natural language, even for users with no coding background. The strategy that we developed in the simulation transferred directly to living cells, a form of a tissue printer that doesn't require a physical scaffold. Next, let's zoom in into the subcellular scale. Rho GTPases are molecular switches that control the cytoskeleton. For example, RAC drives protrusion and Rho A drives contraction. In this experiment, FARO continuously segments the cell edge and projects light onto any chosen site. Activating autogenetic RAC pushes the cell upward, then redirects the protrusion to the right as we move the stimulation target. Switching to optogenetic Rho A, the illuminated edge accumulates active Rho A and affectin, then snaps inward. By automating these experiments, FARO lets us probe and perturb cytoskeletal responses locally, reproducibly, and at statistically relevant numbers. Using the same Rho A actuator, we could also create artificial signaling waves, as has been observed naturally in cells. Using FARO, we can now recreate them on demand. This gives us a controllable ground truth to, for example, parameterize reaction diffusion systems that govern these dynamics at the cell cortex. Zooming out, let's look at some applications at the tissue scale. As an example, when a cell dies, its neighbors fire a protective ERG signaling wave that shields them from follow-up apoptosis. Here we track a chosen cell and target it continuously with UV light, inducing controlled cell death. As the cell is extruded, a radial ERG activity wave sweeps through its neighbors. An interesting question is how the signal is propagated. Is mechanical contraction alone enough to trigger the ERG wave without apoptosis? We locally induce a contraction in the tissue, keeping the stimulation centered on the selected cell even as the tissue deforms. Again, an ERG wave can be seen propagating outwards, confirming that mechanics alone can drive the signal. FARO stack is built on open standards. A modular Python pipeline handles segmentation, with Stardist, CellPose, or interactive pixel classifier convpaint, followed by tracking, feature extraction, and the stimulation logic. The pipeline communicates with the microscope control software, here Pymoncore Plus and Micromanager, through the hardware-agnostic USEC schema, which describes acquisition events as a kind of metadata. This decouples experiment logic from the hardware. The same protocol can run across multiple microscopes from different manufacturers, even with different microscope control backends. Users interact through an Apari-based graphical user interface and Jupyter notebooks. The pipeline building blocks, the segmentation method, tracker, feature extractor, stimulation strategy are modular and can be easily swapped in and out with a single line of code, letting users easily assemble custom experiments without rewriting the entire pipeline. All data is saved in open formats: OMI-SAR for images and masks, pandas data frames for quantifications. From subcellular cytoskeletal dynamics to single-cell migration and even collective tissue behavior, FARO provides a unified platform for automated optogenetic perturbations across biological scales. All code is open source and available on GitHub. We invite you to try it and adapt it to automate your own experiments.